Welcome to FMSP Online Revision. This session is for OCR D1 and the topic we're looking at is graph theory. So we're going to start by having a look at the specifications for graph theory, and then we'll work through a couple of questions just to see if we can help you get as many marks as possible when it comes to the exam. So first of all, the specifications. So candidates should be able to understand the meaning of the terms arc or edge, node or vertex, path, tree and cycle. So it's interesting here because there is a lot of other information given to you in your textbook and stuff, and a lot of other definitions, but just be aware that these are the ones that you need to learn. So some of the others are things like connected graphs or simple graphs and things like that. They will actually often be given to you in a question. So then in part B it says use the order of the nodes in a graph to determine whether the graph is Eulerian or semi-Eulerian or neither. So you do need to know about a graph is Eulerian. So remember, Eulerian if all nodes have even order. Semi-Eulerian is when you have precisely two odd nodes, and then if it's neither of those, then it is neither. And then in part C it says solve simple problems involving planar graphs, both directed and undirected. So again, if you think about a planar graph, and we do need to know what that is. Then if I take a graph which has, say, got 4 nodes, then if I connect all the nodes up like that, the only way I can connect these two whereby it's planar is round like that. So planar graphs, arcs or edges should not cross. So those are the things that we need to know. So let's have a little look at a question. So again here they explain that a simple graph is one in which vertices are directly connected by at most one arc and no vertex is connected to itself. So no multiple arcs or loops. Connected graph, it explains, every vertex is joined directly or indirectly to every other, and a simply connected graph is one which is both simple and connected. So we've got to first of all explain why it's impossible to draw a graph with exactly 5 vertices of order 1, 2, 3, 4 and 5. In part 2, explain why there is no simply connected graph with exactly 5 vertices of order 2, 2, 3, 4 and 5. And state which of the properties simple or connected cannot be achieved. You've then got to calculate the number of arcs in a simply connected graph with 5 vertices of order 1, 1, 2, 2 and 4. Explain why it cannot be a tree, and draw a simply connected semi-Eulerian graph with exactly 5 vertices that is also a tree. By considering the order of the vertices, explain why it is impossible to draw a simply connected Eulerian graph with exactly 5 vertices that is also a tree. Now it's very wordy, isn't it? So try not to get put off by all these words, because some of the questions are quite quick to do. But that's part 4. It goes on because it then says in the graph below, the vertices represent buildings and the arcs represent pathways between the buildings. And in part 5 of this question, it says by considering the orders of the vertices, explain why it is impossible to walk along the pathways in a continuous route that uses every arc once and only once. And write down the minimum number of arcs that would be needed to travel would need to be travelled twice to walk in a continuous route that uses every arc at least once. So as I say, it is a very long question, and it's bringing in most of those points that we looked at in the specifications. So let's break it down into some bits and explain first of all why it is impossible to draw a graph with exactly 5 vertices and the order of the vertices are 1, 2, 3, 4 and 5. So hopefully you will know that the total order of any graph is always even, which means that you cannot have an odd number of nodes. So you cannot have an odd number of odd nodes. So that is what breaks down in part 1. We've got 3 odd nodes here, and that's not allowed. In part 2, it says, explain why there is no simply connected graph with exactly 5 vertices of orders 2, 2, 3, 4 and 5. State which of the properties simple and connected cannot be achieved. So you've got 5 nodes, 5 vertices, but one has order 5. And that's the important thing for you to see in that particular wording, is that you've got here a vertex which is order 5 and you've got 5 vertices. So that would need to be connected to itself. So if it's connected to itself, it's not simple. You would need a loop. So that is the bit that it cannot be achieved. So hopefully that makes sense. And then in part 3, it says, calculate the number of arcs in a simply connected graph with exactly 5 vertices, and the orders are 1, 1, 2, 2 and 4. So if we add the total order, so we get 1 plus 1 plus 2 plus 2 plus 4, then that gives us 10. So if the total order is 10, then the graph has 5 arcs. 5 arcs or 5 edges. And then it says, hence explain why such a graph cannot be a tree. Now you should know that if a tree has got n vertices, it will have n minus 1 edges. So a tree, a tree with 5 vertices has 4 arcs, 4 edges, whichever word you like. And we're using a mixture of all of them really, aren't we? So that means that we've got 5 arcs here, so it cannot be a tree. So maybe we better and ours has 5, so it's one mark for just mentioning here about the total order being even, so you can't have an odd number of odd ordered nodes. 1 mark for seeing that one of these nodes vertices had order 5, so it needed to be connected to itself, and 1 mark for the fact that that meant it couldn't be simple. And then you got 1 mark here for working out that the graph had 5 arcs, and 1 mark saying that of course a tree has got 4 arcs. If it has 5 vertices, then the tree will have 4 arcs. In part 4, we're asked to draw a simply connected semi-Eulerian graph with 5 vertices that is also a tree. Now there will be different ways in which you can do it, but remember, if you've got 5 vertices and it's a tree, then you're only needing 4 arcs. So I'm going to put my 4 arcs in something like that. So that is a possibility. That is a tree. It's simply Eulerian, semi-Eulerian, because we've got an order of 2 here, an order of 2 here, an order of 2 here, so each of these have order 2, and these have got order 1. So that's the important thing. You see, it had to be semi-Eulerian as well. By considering the order of the vertices, explain why it is impossible to draw a simply connected Eulerian graph with 5 vertices which is also a tree. So now a tree will also always have 2 nodes of order 1. So any tree, and think about any tree, because of the fact that you won't have cycles and things, any tree will always have to have 2 nodes of order 1. And of course an Eulerian graph has all nodes of even order, so it just can't work, can it? So not possible. So there were just 2 marks for that question, but you do need to try and write it down as carefully as possible, that statement. So there was 1 mark for drawing your semi-Eulerian graph, which was a tree, and then 1 mark for this statement. And we'll just come to this last bit of this question. It says, in the graph below, the vertices represent buildings and arcs are pathways. By considering the order of the vertices, so I'm just going to write in brackets here the order of each of these. So we've got 3, 3, 3, 5, 3. So all vertices have got odd order. So you've got 6 odd nodes or vertices. So it cannot be either semi-Eulerian or Eulerian, can it? So it's not Eulerian or semi-Eulerian. So that's important. So that means it will be impossible to walk along the pathways in a continuous route. So I'll just put that in. So what could we do to help it now? So it says write down the minimum, and this word minimum is important. So we're not told that we have to start and finish in the same place, so the minimum way in which we could do it is just to take 2 pairs of odd nodes and join them up. So for example, we could take this pair here and this pair here. Now if we do that, then that means we've made our graph semi-Eulerian, so we'd have to start at either F and finish at E or vice versa. But the important thing is we don't have to repeat 3, we only need to repeat 2 to make it semi-Eulerian. So write down the minimum number of arcs that would be needed to be travelled twice to walk a continuous route. So that is that. So 2 marks. So 1 mark just for explaining that you had 6 odd nodes, so it couldn't be either Eulerian or semi-Eulerian, and 1 mark for the fact that we had to repeat 2 arcs. Okay, we'll have a look at part of another question. Now, at the beginning of this question, it did again remind you about what a simple graph was, and what a connected graph was, and what a simply connected graph was. So it did mention those. But this time we're told that the connected graph has 4 vertices, A, B, C, and D, in which A, B, and C have order 2, and D has order 4. And what we're asked to do is explain how you know the graph is Eulerian. And then we've got to draw an example of such a graph and write down an Eulerian trail. So in part 3, if we look at that then, so it is always going to be Eulerian because all vertices or all nodes have even order. So that's the important first part. And then we're asked to draw an example of the graph. So you've got 4 nodes, 4 vertices, A, B, C, and D. A, B, and C have order 2. So that's A. And we'll call that one B. And C and D. So A, B, and C have order 2, so that's that, and then D has order 4. Now in order for D to have order 4, it can't be connected to any of the others because that would increase the order of A, B, and C, so it must be connected to itself. And now it says write down an Eulerian trail, so I'm going to start at A. So we could have A, B, C, and then we'll be at D, and then we'll go round D and come back again, and then back to A. So you should show these twice. So this is the loop. So you've got 1 mark here for making the statement that all vertices have even order. You've got 1 mark for drawing a graph. Now your graph may not look like that, but it should be sort of essentially the same. And then you've got 1 mark for writing down an Eulerian trail for your graph. So again, it may be slightly different from that. And then in part 4, it says a graph a graph has 3 vertices A, B, and C of order A, B, and C, little a, B, and C. What restrictions on the values of A, B, and C follow from the graph being simple? So if the graph is simple and you've got 3 vertices, then you can't have any multiple arcs, or you can't have any loops. So A, B, and C can only have value of order 0, 1, or 2. So any of those, they can't have been connected to more than 2 others. We don't know that it's connected, so it is possible that they have order 0. So that is part A. And then in part B, it says what restrictions are there to make it a connected graph. So remember, if it's connected, then none of them can have 0 order. So A, B, and C cannot have order 0 because otherwise they wouldn't be connected. And then in part C, semi-Eulerian. So remember, semi-Eulerian means that you have precisely 2 odd nodes, and that means that you would have 1 then that was even. So there is 1 mark for each of those. So I'm going to stop the session now and just remind you, as always, to work through as many questions like this as you possibly can.